Awesome. Good to see everybody on. My name is Kevin Kowalczyk. I'm the founder CEO of Chemical Q Device. This is discussion 117. This is Thursday, January 11, 2024 for efficiency metrics, single QML algorithms versus parallel QML algorithms. So if you're just joining this, is basically it's trying to really pinpoint the exact advantage of running parallel quantum circuits versus a single one. And that can in these days only be done with many experiments and tables of data. So basically picking off from last week is, I'll show you the kind of diagram that kind of like ended things with RAM and runtime. And it's basically varying the number of variable gates to find out what was the most efficient circuit for a single circuit, second circuit, or double parallel algorithm, triple, so on and so forth. And basically, there's some kind of thought behind this sequential method. So if you've ever done neural networks, you can do sequential, which is, more linear in nature. And the more common one is the module. So looking through a bunch of the data, it looks like that does have an effect, right? So torch.nn.module does help. And especially if it's lower circuits, if you have, say, like a 4-qubit circuit, with like a 4 rotational layers, something like that, it tends not to perform well. So the good news is just to run in module and to avoid very small circuits, because you'll get all kinds of fluctuations. So I kind of pinpointed that. The other thing is these rotational gates, these rotational trainable gates, basically, they have a fixed seed. Configuration can vary slightly from, what's shown in the diagrams, but basically, kind of Penny Lane guided me through what these exactly are, and they're available in the notebooks, which I put up on GitHub. So this is all done with Python, Penny Lane, PyTorch. Thomas Bromley is the one that created these two Keras and Torch notebooks, and you can, create whatever architecture you want, keeping in mind that quantum circuits are quite involved themselves. So maybe sticking to parallel circuits might make sense at this point. And OpenAI is being used, for machine learning and notebook clarifications. It's a good tool for that. So this week is going to study, focus more on the epochs, so comparing single circuits versus, these others. So there's, you could double parallel circuit, so on and so forth. Now, the preference I gave with this is whatever was the best single circuit algorithm. And, for this week's study, it's 4 rotational Y gates and then 5 trainable rotational Y gates. And like I said, with the second one, it's somewhat randomized based on the template that I had to use. But they're all the same. So it's the same algorithm for single circuit, double, all the way up. And efficiency metrics. So it's important because when you do these runs and it's based on something other than time, that can have an impact. So I developed some of these efficiency metrics for training loss, validation loss, efficiencies for those two, and also standard deviation of, say, the difference in the train and the validation loss for each of those. So, okay, so this is picking up from last week. So what the study shows is basically increasing. So this is a single set. These are all single circuits to the left. And then the second one is going to be a double wide or double algorithm, and then so on and so forth. Now, in each of those, they kind of had their unique, algorithm that they preferred. And like I said, to give the advantage for the single circuit in testing, I picked this. It's the one I mentioned before, this 4 rotational Y embeddings, and then 5 rotational trainable gates for all the studies for this week. And, basically you can see with this is what the effect of adding. So each is a set. So these are single circuits. This is single circuit. I'm sorry, this is 2 parallel algorithms, 3, 4, all the way up. So you see the effect of, adding additional rotational gates. Now, it's not believed that it's not anywhere close to exponential, because if you do anything with, quantum programming on simulators, you'll quickly know that increasing the number of these, qubits on circuits, it quickly goes exponential in RAM. and it hurts with runtime too, but especially with RAM. So it can become an issue if you go far, so say hundreds of qubits, these types of things in single circuits, and without circuit cutting or doing parallel quantum circuits, it's an issue. And so basically starting off here is all of these are single runs. Okay, so there's 15 single runs, right? So each of these have their own notebooks. And what happens is, you'll see that the black and the red are from the single circuit. And then what happens with these is the majority of the time you'll see this green. So the yellow and the green is for a double circuit. Now, the reason why I chose to focus in specific on this one is because a single circuit and a double circuit have closer time overlap. So the single circuit's always going to be faster. So and that's why I also did efficiency studies to minimize the effect of, say, 50 qubits, running on a single circuit is a lot faster than 50 epochs versus 50 epochs on, say, like an 8 parallel circuit. And, so you'll see with this, and the ones that stand out the most to me is basically, you see these early greens. So it's an efficiency is basically 1 over runtimes times lost plus a coefficient in order to scale it correctly. So the higher the better. And you'll see, so the double circuit did better, in this particular study. Now, the thing with this, especially with parallel quantum algorithms, is they tend to avoid these like spikes that you get. So in this case, the spikes are good, higher efficiencies. And, it's apparent in these tables. So I'll go across one of these. So this upper table here is basically, again, they both use the same algorithm. It's just the bottom one has 2 in parallel. So in this top one, it's very common. And actually, for this one, I had to install, you always want these 4 metrics. You want training loss, training accuracy, validation loss, and validation accuracy. And then in order to get a good idea of, its fluctuations, or like, you want to minimize those. So I took the absolute value of the loss difference. So it's this training minus this validation loss. And if one was bigger than the other, it always gets that difference using absolute value. And then, so what's done is basically, so there's 15 runs, and then I take the standard deviation of all of these losses. The lower is better in this case. So runtime typically comes out in seconds. I convert it to minutes. And then training loss efficiency and validation loss efficiency are these, the factors that I mentioned before. So 1 over runtime times loss of the training loss. And then same thing with the validation loss, 1 over loss times runtime to get these metrics. So efficiency is higher or better, and then RAM lower is better. So this first one, what pops out is runtime and gigabytes are the same. And you can see kind of where they cut off. So the runtime, so say we go up to 3.62 here and we end at 3.6 here. Okay, so you can go, line by line, and it's, that's typically the case, is the double circuit does better. So better, it's faster runtime, and then you also have lower RAM. You're just going to have it, and this is kind of like the 2 gigabytes, and these can fluctuate like 0.1 plus or minus, and you try to get it right after the run, but they in general they're accurate, but they fluctuate just by small amounts. This is through like Colab. Now for the second one, basically what stands out, and here's the thing, is if you're spending more time processing, you have to count for that, right? So you just can't say at 15 epochs at 0.0087, which was a lot better than the single circuit at 100%, because it's spending more time processing. So that's what the efficiency metrics take care of. So these two, so training loss efficiency and validation loss efficiency, in order to kind of level the playing field, because this one's getting done with experiments earlier, because it doesn't have as wide of as algorithms. So what this one excelled at is, obviously this is the only run, the last one, to get 100%. And then the standard deviation was lower. So it went from this 0.0282 down to this 0.0265. And then I highlighted kind of like the low one here. And, just when you run these, you see that if the algorithm's smaller, is, single circuit, they tend to fluctuate more and the losses don't tend to be as good, especially at this epoch range for both of them. So then you see efficiencies here. So the high of 0.81 for training loss and then a high of 1.2. So it's an arbitrary scale. And, when I do the final write-up, I'll show you exactly, the equation that was used. So basically what this shows is, when you do single circuits for like data set mapping and classifications, you get this, well, obviously it's a high initial validation loss, but it shouldn't be going up and down, right? So this just goes to show that it's not training well, and it's not a small algorithm, right? It's this, it's 9 total layers of gates. It's just that, I think a lot of people would try to pick the correct epoch in order to get their single circuit performance. So that's an issue. So again, like nothing that I've seen in going up with qubits in this model has helped, and especially that's where the exponential RAM and runtime. But you could see, over the course of this, and I plotted these, this statistical modeling here. For the first one, the R squared coefficient. So if you remember from, if you don't do this every day, 0.535. And then so for the 8 layers, 0.887. So it's basically saying this bottom line, correlates a lot better, with more algorithms in parallel. So the charts that correspond to this, and again, these are good studies because they're similar in time, so you want to effectively take care of that with efficiencies. And it was the same as before, but now this is 11 runs. So one run is one epoch, and you take that last epoch or that only epoch. And the 51 is I take the last epoch off that. And you'll see that the average here for runtime and RAM is going to favor the smaller circuit. And then for here, the efficiencies were actually quite better, going across instead of 1 through 15 epochs, now expanding it to 50. So you see the average here, 0.42, and then for validation loss up from 0.47 to 0.54. So these are thought to be accurate. And, you always want to account for things because you think, total device time, how long are these running, these types of things. And then so, this is for 3 and 4 layer, and nothing out of these two kind of stuck out the most. And this is for 5 and 6. And then here at 7, so this is 7 parallel algorithms. So you have their standard deviation of the lowest, so, that's, for this particular algorithm or architecture. And then the other one that kind of pops up is this, the last one, which is 8 layers. So you have, the best overall minimum loss. And this is part because it's, it has more time to process, right? And the other metrics with, especially the efficiencies kind of like put these back into perspective. Now, here we go here. So this is showing that number. So this is this 0.000199. And like I said, it takes the difference between the training and the validation loss, and it takes the absolute value of that, and then it's the standard deviation of that, right? So standard deviation, you only get a single line of data, and it just, you're doing it on that specific one. So this is the case, so the most with 7 parallel algorithms. And then, the correlation was pretty good as far as, this is a logarithmic plot that, it correlates 0.755 over the course of single algorithm, second algorithm, these types of things. Okay, so the next one is basically this is RAM stays constant for most of these epochs. Now, if you ever do machine learning, if you only give it 1 or 2 epochs, chances are that RAM isn't going to be the true RAM that's needed to do, evaluate loss function, update parameters, those types of things. And that's what you see here at 1 epoch, but you see 5, 10, and especially at 10, all of these are the same. So these are the same, these are the same, these are the same for RAM. And so runtime goes up. And again, if if you determine you want to run a certain number of parallel algorithms, that's the case. You just have to be aware if there is an increase in time or runtime, but it's nothing near what you're going to experience in increasing qubits in a circuit. So that's where the priority goes towards parallel algorithms. So this is the best of everything. So this specific slide, so it's the order of highest performance. So I ranked it 1 through 8. So each of these saw 11 different, 11 different experiments. So for the first one, this training loss, you'll see, for 2 layers, that's the given value. But the one that really matters is the training loss efficiency, and that's how I rank these. So you see it goes 2 layer, 4 layer, and these are all in parallel, 3, 5, and then the single circuit here. So the higher the better for efficiency. And it's basically, and this is a good study because, this is a range of epochs that people will run at. If you want to run, 5 epochs, 10 epochs, those are all in the study going up to 50, every 5. So that's what got the main ones is basically these two, for the double parallel algorithm was the most efficient out of the study. And you'll see here with runtime and RAM, the 6.02 and 2.8, that's always going to go to the single circuit or the algorithm that doesn't have as much, behind processing. Now, for these other ones, the 6, 7, and 8, they perform well, but keep in mind they also take a lot of time. So your 8-layer algorithm clocking in at half an hour, for this particular one. These are run on high RAM CPUs, but it kind of gives you like a gauge of where things are at. And the last part here is basically, I wanted to do a study as far as scaling it up as far as, okay, if I'm using 30 minutes, worth of this 8-layer parallel circuit, what does that equate to for a single circuit and this double circuit? And it turns out that actually, if you go high or really high in epochs compared to the rest of the study here, is that the effect of the machine learning actually has a greater effect than the parallel algorithms. So, there's a range and there's an operating range for the algorithms. And like I said, it takes a while, to get to zero loss. Typically that's a very hard thing to do. But in these is basically saying, it took 210 epochs around the same time for single layer, 150, and the factor is about 1.4x as far as time needed. So you kind of judge these things. Now, the 2-layer one actually did have the lowest loss, and it really slows down, towards the end. So if you're going from like a 0.050, something like that, that's going to go a lot faster to get to your 0.049. But it is, in these cases here, if you have a 0.0007, it's going to slow down. So we're talking about machine learning and this, the landscapes, so basically, when you do these at a constant learning rate, in order to get it right epoch after epoch, it takes longer in order to get these lower losses that the computer's prediction is matching the actual values. So yes, it did have slightly better, training loss, but and this is another thing too, is the, single algorithms, they tend to have this, greater loss difference. And, I was trying to get the runtimes as close as I could. But, that's the moral of the story is where do you want to process? It makes sense, especially in normal working range of epochs to run parallel algorithms according to the results. And then as the number of epochs increases, the effect of the machine learning appears to take over, compared to fine tuning the algorithm. So this is this for the slides. Now, I saw a couple people kind of hop on here. Are there any questions? So again, there's on the GitHub, there's 5 weeks of studies with this. And, basically, it's clearing up to definitively, if I were to say like, how many epochs do you want to run? I'm getting closer to as far as having these equations. It's data set dependent, data set size, those types of things too. But there's different statistical models that, to people that, you can come by in order to say, okay, how many layers should I run in parallel? Go ahead, Ron.
Hey, Kevin. Yeah, I just again was wondering if you have if you're keeping track of the circuits, making a copy of the circuits for these various runs,
Yeah. So
so
if
we
you're
can
talking,
have a visual comparison also of that.
yeah, yeah, if you're talking about previous experiments, like the past 2, 3 weeks, they all are loaded, and it takes a while to go through. But I think it's pretty straightforward. Any other
Okay.
questions? And when you're going through quantum computing, many people go through Qiskit just to learn all the basics. But it helps to run. I was asked a question as far as helping somebody with a different field with their studies, and the demos are always the first place to start. Like Penny Lane has abundant demos. So if you're in a specific field, you're looking for certain strategies to solve problems that have already been done before. And if that's what you want to focus on is quantum machine learning, is they have discussion forums for Penny Lane. Qiskit's okay. I wouldn't say that that's the as big of an effort as with Penny Lane, but it's just working the way up.
So like on this sheet you're showing you're listing what you start with 10 qubits, 2 layers, and go through variations of that. Although you go 2, 4, 3, 5, back to 1. Is that just looks
So
like it
it's
goes one
it's
through
arranged
8
by
layers.
top efficiencies. So
Okay.
yeah, so I
Ah,
ordered it 1 through 8, and then this is how they sit in the based on it's basically at a specific time, how much loss are you getting? The lower, the better. So loss and runtime, they both run down. Lower is better. So basically, it tries to equilibrate between all the different studies, as opposed to just saying like, I ran 50 epochs for this smaller circuit and 50 for another, but the
yeah.
bigger algorithm's going to take more time.
But as far as the layers, they're just duplication of the circuit box sequentially.
Not sequentially. Yeah. So this is it's
Oh,
torch.nn.module. So it splits it. So it actually sends the same data to all the parallel algorithms, and then it takes that output and concatenates it. So
so when you're saying 2 layer, you may actually have 2 independent sets of 10 qubits. Is that what you mean?
yeah, they're basically they get the same. It's the
Okay.
same. That's how it's like torch.nn, kind of like the basics is it splits it, meaning it sends everything. So if you're doing two in parallel, they get the same data set coming in, same instruction, and then especially in the working range of epochs, that tends to be more efficient than running more epochs of a single circuit.
Yeah, but so for 2 layers though, you actually have 20 qubits involved. They're just in 2 separate groups.
Yeah, right. I call them effective parallel qubits.
Yeah, okay.
So, and you can measure it in terms of effective parallel gates too. So that's a useful metric too.
Okay. And you're keeping documentation on the circuit like in a high level detail like rotational with or with no or medium or high level of entanglement. Is that how they do it?
Yeah, so I think 2 or 3 weeks ago, I did an in-depth study with all CNOT gates, Hadmar gates, and the main thing that's helping is it's the mapping of the data set across the qubit. It's the sphere, like these are pure states, there's no quantum noise. So it's mapping it across the sphere as opposed to these other quantum effects that, you know, I've tested it ad nauseum, and this is, I don't know, third, fourth, fifth series that I've done in people in literature too. But the primary, mechanism behind all of this is they call it quantometric learning, or basically separating data on different parts of the sphere as far as you can, like a zero loss, 0 point, however many zeros on the opposite sides of the block sphere.
So it's still like a quantum embedding learning cycle.
Yeah, and rotational
Wait,
gates help,
yeah, yeah, okay.
most of the time. That's been the case. So I think 7 out of 8 of these, you know this algorithm that was used across all these studies, this was 4 rotational Y gates for embedding, so that has inputs, and then another 5 are trainable that don't take in inputs, but they get adjusted like quantum machine learning over time. So
Gotcha.
yeah, and Maria Schuld at Xanadu and other researchers too. They said it's all in the embedding, but yes, you can fine tune the embedding. But if the embedding is not correct and you go straight to using your variational algorithm, your gain is not going to be in there. Like the embedding has to have loss convergence that's pretty low, meaning like within 4 decimal points or something like that, and then add on the trainable gates, and then that's been proven the most effective.
Sounds good. Thanks.
Anybody else? And so the application here is classification, data set mapping, and myself, like the rest of the world, when you have an abundance of data, like you only want to change one thing. So keep everything the same, except for just change the number of layers. And that's basically what this study was, analyzed it at different epochs. So the more you can do that, the more, as the data sets get harder and harder, the more you can kind of like pinpoint as far as saying like, these are the great results that we're getting, but then we have to further understand that how it applies to all data sets. And I guess the key words are basically practical, because all of these, there's no GPU here. Actually, there's a PyTorch penny lane limitation with running a GPU at this stage. So high RAM CPUs, like a Google, it runs twice as fast as a regular CPU. I didn't get anywhere close in these experiments. I got close with higher qubits, but basically, 11 gigs of RAM, and I have like 50, right? So I guess for kind of like clarification, like a laptop might have 16 gigs, but that's for everything. So yeah, this is important. This study is important because basically, if you scale with a bigger data set, um, and you don't have the luxury of you're basically on par with what this is, because this is a more simple data set, is that knowing the effective range, which is pretty wide for the parallel algorithms, as opposed to like going many epochs with a smaller algorithm, um you know it helps, right? And I think the biggest thing is this, the standard deviation of this loss difference, or the absolute value of it, is basically, you'll see that a lot with the single circuits, is all throughout, if it's a single epoch run or 50 epochs, that's typically a bigger value, meaning that the loss between training and validation is wider, which is um, not preferred, especially if you're trying to build onto an algorithm, like you have an embedding and then you're building on with rotational gates or whatever gates you want to use. Any other questions?
This is interesting, but it's way out of any range where I feel as if I can ask questions. So, thus the silence.
Yeah, I mean, it's a lot of machine learning. So,
Yeah.
you know, it,
And,
it's a lot.
Kevin, all of your experiments are where they use the quantum elements as a replacement neural net layer, or it's one of the layers in your machine learning stack, right?
Yeah, they
And
call
the
it, yeah, torch layers, is the
yeah,
penny lane term. And yeah, it does its quantum thing and then it goes back into classical bits.
and then it's and the machine learning, everything else is just the same, just like machine learning trains the values of the normal neural net layers. They train the embedded layers of the quantum, whether you're using like an array of RYs or whichever set of gates you're using. You're just training those parameters.
Yeah. I mean, at this
Yeah,
stage, there are some limitations with the different types of gates you can use based on inputs and outputs. Like I said, I have to use it's called QML.angle embedding or QML.random layers right now, as opposed to using
yeah.
QML, a straight QML.Hadamard or .ry, those types of
Well,
things.
yeah, and the Hadamars are static though, so the only thing you can control are the rotational angles, right?
Yeah. And
Those are your quantum parameters that get trained. Whether or not you add the Hadamars or C knots, those aren't trainable. They just change the characteristic of the quantum circuit and gives you
yeah.
a
And
different response.
you can get very little loss with just an embedding, right? So it's just taking in the
Cool.
inputs of the data set, and it's just working down. So if you're familiar with the loss function and the loss curve, and it's easier, when you first start up here, if it like in an ideal case, so that a first epoch to second epoch, you might jump, like 0.12, but then you're closer to like 50 epochs. Now it's like 0.002. It just gets harder and harder getting closer to the bottom of the well.
Yeah.
So yeah, I mean, in basic terms, yes. I mean, there's programming things that you have to be aware of as far as you can't do everything, at this stage. And obviously, the GPU support would be awesome. And but in
So I
theory,
know
yes,
you've
everything's
been doing
packaged.
this for quite some time. So have you gotten a sense of whether just like pure RY gates versus RX, RZ
Yeah.
gates make a difference compared to just a random mix of rotational gates?
I did have a good it was a trainable layer. It's called basic entangling layers. And
Sure.
the basis or the one that it comes with that you don't have to change is X. So I changed it to Z and Y, and actually Z for that particular case worked the best. And across all my studies, in different models, it's always been Y, like at
Yeah.
each RY, or in these cases, it's RY embeddings and RY trainables. But yes, there are many possible combinations, and I think kind of,
I mean, did you ever do any where the circuit block has both RY, RX,
oh
or
yeah,
a combination? Okay, cool.
yeah, you could do, yeah, because I guess in that specific case, if it was RY embedding to RX, trainable layers, so there's nothing holding that back. I When I first started this, I did a lot with the penny lane. It's convolutional neural networks, which is quantum convolutional. And I tried many combinations of bases and different types of gates, and it all came down to yes, the trainable gates help, but if you're embedding, you have to test the embedding to the point where it's just like ad nauseum, and then build onto that circuit.
So, I have a naive question, very naive. what do we expect to gain by using RY instead of thresholds, classical thresholds?
That one I'm not, you said classical thresholds?
So machine learning is, from what I understand, you've got these artificial neurons and you adjust the thresholds or adjust the formulas for when they fire.
Yeah.
What we're doing here is we're adjusting the RY of certain qubits. What's making this? What's the opportunity here that we don't have when we're doing it with classical?
Yeah, so the main train of thought is this exponentially large Hilbert space that's available on the surface of the sphere because we're in pure states, with simulators. And there's a paper by Seth Lloyd, and this is MIT and other researchers too, that basically claimed that they were able to separate data sets on complete opposite sides of the sphere, the block sphere that represents the qubit. So that's the main thing. And I don't, that understanding it more fully and saying like this, data set perfectly, fits for this type of algorithm, it's still developing. Now, on the classical sides of things, it sounds maybe we're talking about, is it weight decay? So limiting the max parameter values for classical.
Well,
I think one of the phenomena is that because they are they are full qubits, they respond to the DiVincenzo criteria. You can imagine that you're able to do super dense coding. This is like the situation where you have 3 qubits. You can actually, on the 3 qubits, encode a 2-dimensional image that is like a 8x8 image. It's crazy. So there's got to be something like that going on here also.
Yeah. And I guess that's the bigger thing. If you're talking about, nodes and neurons and these types of things, is yes, it's like if it's fully connected, it means that node's connected to all the other ones. And then you could place, you could bias a certain part of a neural network to basically say this one is allowed to have higher weights, meaning like when it goes through every time that this is more important. So I think the biggest thing with quantum machine learning is thinking about, the block sphere, how can this be used the best, with embedding and then training later, or adding training later, like, that needs to be like, even though the results are really good and other people have gotten good results with it too, and fine tuning it just has to be like, okay, we understand this for this type of data set or a different one too. And I just think that's the most important thing is this. Maria Schultz said this: you can get by with just an embedding, and even not. They've done research with training the embedding and these types of things too, and it's really an arbitrary thing because even there's this single qubit. It's data re-uploading. So basically, getting by with 1 or 2 qubits to classify images. And they don't take a traditional approach as far as saying this is an embedding layer, meaning that these inputs are coming in here, and then this is a trainable layer. They just treat everything kind of like, this is what, this qubit is being processed with these types of gates. So yeah, there's different thought behind, some of the different applications.
And I'm just guessing at that, but and I know Kevin many sessions ago was showing how quantum QML in like image processing was encoding images on just a handful of qubits. So it's got to have something to do with that, where it's taking advantage of the super dense coding.
Yeah, I can imagine. I picture.
Go ahead.
Yeah, well, you think of one of your, one of your graphs where you have like a 4x4 thing and you got your wonderful little rotational icons in there. If you could change those rotational icons to a dot of different sizes, you could actually draw a picture on the matrix. Just by, it gets very tedious drawing a specific picture, but it's possible.
Yeah. Yeah, I think they describe it as there's the kernel method, there's the variational circuit method, and in different cases, one might be better than the other when you cross like a certain, threshold, basically. And some of these, it'll actually, a pixel goes to the qubit. So there's an IBM Qiskit demo that's actually quite fun to play with. And try to think how many qubits this was, but basically it's a 2x8 image. Or 2x4, so that's 8. So they're using 8 qubit circuits with this, and that's a really small image, right? So what's the, what's practical? Even if it's like the best absolute results to do it like that, to map things onto qubits, and as opposed to the classical algorithms, there's different approaches. But at one point, Xanadu did put in the forum that early on, I asked, what's the best method to use for image classification? And they did point me to it's Maria Schultz's variational quantum algorithm. It's a demo. So.
Yeah, and to be honest, probably what I really believe is using a quantum circuit as a trainable quantum circuit as a replacement layer in a machine learning neural net is probably just more PFM than anything else. I don't think anybody really understands why it works. It's just like the guy who during COVID he had nothing better to do, so he built a little circuit. I think it had one transistor, a couple other components, and he had the ability to put a signal into it and take a signal out of it. And he used that silly little thing as a small layer in one of his machine learning projects, and he was able to train it. It's like, can't explain why it works though.
Is that what's PFM?
Pure fucking magic.
Okay, all right. I figured it was something that
Sorry.
Yeah, I mean, if it's taken, because the whole industry is moving towards, GPUs and quantum algorithms, so this is, basically classic Terra Quantum AQ, BASF, Google Bard, and they're basically saying like, we can do stuff, with quantum algorithms on classical processing, so it took me a while to get over that hurdle and thinking that it's not unique to any device. As long as you can run the algorithm, then you can run it, right? If it's a simulator, anything. So, there was a recent, basically it's a, quantum inspires whatever. And I believe this is Terra Quantum AQ, but there's other companies too. So I think especially like the practical aspect of machine learning, there's many parts involved, right? So these are continuously updating. This is not just running a single problem. This is just, if you have say with these, like the batch size is 5 and like the training size is like 150, so 5 into whatever, you're running, multiple batches before even getting to the first epoch, which is normal. Most people don't, I don't think, run the whole data set through this, an epoch, and that's not as common. But there's all these working parts. I think, whether you think quantum computers are coming in 3 years or 5 years or 7 years, like you have to prove these things, proof of concept. I used all these algorithms. And the number one thing you could do with this research that's not really debatable is comparing quantum algorithm to quantum algorithm. And, that's a huge thing to do. I think for anybody getting started is, besides benchmarking devices, runtimes, is, you can prove, which quantum algorithm works better than another. So without much, without much experience.
At certain sizes, for sure. Yeah.
Yeah. So that's my understanding of this all. And I've, researched kind of like all the limitations of what it would take using other methods. And, say if there's this thing that swoops in, all this research goes directly into what other, technology can run it. Right. So that's why I encourage other people, because, if you're running on, quantum simulators, a lot of this is building a knowledge into whatever, say like you figure out like it's for sure only the embedding and these specific parts as opposed to other quantum effects. It just makes sense. Like you get really good data now while you can. And if you're listening to this on the recording, there's a whole slew of Qiskit. Most of the most recent research is with this, penny lane, these specific demos related to algorithms. Now, I did a whole thing on Qiskit that shows you how to actually run in Qiskit. So this is like different demos, how to do graphical composer, how to print those, all that kind of stuff. Which is fun. So it's in the Qiskit folder in under code in the repository. So I would highly suggest that to anybody. Like you have to know the basics, and I use the Feynman approach. So I teach and then I look to make better analogies to it. And you would be surprised just the benefit of talking to other people, like if you were working at quantum. But helping other people, teaching other people too, can significantly increase you need that core knowledge if you want to be doing these more advanced demos.
Tell me about it.
Yeah, and it's gates and circuits, and it's you don't have to, I wouldn't say memorize. I mean, maybe some people do, like all the Qiskit single circuit gates, and the rotations. But you kind of have to get that, like, okay, this is generally what's happening here, and you're not overwhelmed. So
no, the more you explain something, the better you understand it.
yeah, it's something magical about teaching other people.
Well, what happens is that as you're talking, you're asking yourselves questions. You're trying to articulate it better and better and better, and so your brain is saying, wait a minute, I didn't think of that aspect. I've got to look into that after the discussion, or maybe I've got to think of it now, or it just happens.
Yeah. And if you were to go on to any of the platforms, Meetup or Eventbrite, LinkedIn, I would say you're still probably, going to be at least weeks ahead, if you've taken a couple certificates than most of the people that show up. And some people just want to watch and they don't want to learn or apply it to research. And you can't force anybody to do anything. But, you have to feel confident that, yes, you do know significantly more than other people, to the point of, helping other people and getting to the point of developing your own applications too.
I've taught courses where I was a page ahead of the students.
Yeah. Yeah, it's just get out there and, fully commit to it. Because I think with the whole thing with GPUs and, depending on what you believe with other devices, it's worth it,
I think that statement, Barry, describes pretty much all of quantum. I think a lot of people are just one page ahead of the students. And it's moving so fast. There's so much stuff going on. I think this year in 2024, we're going to see some pretty interesting hardware breakthroughs. I'm still very interested in the neutral atom stuff. Being able to run 256-bit, 256 qubit algorithms directly on a gate machine without going through simulator. And stuff, it's happening, it's coming. And there's so much research going on.
Can a simulator even handle 256 qubits?
No, not even close. I think what's the max?
Well,
Uh,
the traditional method is to cut, so you
Yeah.
cut circuits and then you put the answers back together. And I think Penny Lane's got up over 100 or something like that. These are effective parallel qubits. So it's not, it's not the whole circuit is the same. It's just using that same, good circuit over and over again in parallel. But yeah,
Yeah.
it's a RAM, it's an exponential RAM and runtime kind of thing.
So what's Penny Lane's? It's like 40 qubits is where they're at. 42.
Well, traditional, I mean, when you're talking about quantum machine learning, there's many parts to it, right? So, I mean, even starting with the data set, like once you start to scale up your data set, that, just like in machine learning, that knocks things back. But I think officially, like the Brookhavens, do these types of things, 30 qubits in a circuit. And that's where I say, like, if you can get the performance you want with parallel algorithms, which is what it very much is in this case, then do that. But yeah, it's like you can't do that. It's a different type of limitation, as far as huge circuits.
Yeah, but I'm just talking about Penny Lane's pure simulator. What are they at? Like their top size is 40, 42 qubits, somewhere in there.
Well, there's papers that go, 50, but it's not machine learning. It's
Well,
like,
yeah, and they're playing tricks though. And I'm not talking about machine learning. I'm just talking about a quantum machine simulator. To simulate 40 gates, 40 qubits, and whatever gates circuits you put on it.
yeah, I think it's
Uh,
30. Yeah, that's the last I've heard as far as, NVIDIA
really?
GPU. Yeah,
Okay.
it depends on the problem too, because it's like, it gets really bad, like, as far as resource requirements over 30.
Yeah, so like 32 qubits needs about as much RAM as a very healthy desktop has, like in the 96 gigabytes of RAM, somewhere around there. So to get up to 40, then you need like 1,000 of those machines. 42 or 40,
Yeah.
42, somewhere around
And
1,000 of those machines.
I mean, with the limitation with Keras and PyTorch and no GPUs, so I'm running all these on high RAM CPUs. There's actually NumPy neural networks, and it's shouldn't be too hard to run in parallel. As far as the code goes, shouldn't be too hard as, run in parallel, NumPy, Penny Lane, those types of things. But
Yeah, it's really, I was under the impression that PyTorch had a TensorFlow backend, but they don't. And so the big thing about TensorFlow, it's like NumPy, it's like distributed NumPy. It takes care of all the back end distribution. It's like it'll gobble up as much whatever hardware you want to give it. You can give it a bunch of GPUs, a bunch of machines, a bunch of cores, and it'll break the problems up automatically and get them done out there. But then I've heard that PyTorch has some sort of their own thing, or people are just complaining PyTorch doesn't scale because of this problem. It's like, why don't they just connect it to TensorFlow? I mean, TensorFlow is a pain to do ML in directly. You can, but it was really built to do the distribution, to just distribute the problem out a bunch of an array of machines. It's too bad that they haven't done that.
yeah, there's advantages to both. The Keras demo for this type of stuff with the parallel algorithms, it actually gives much good information, like epoch to epoch. I get like time per step. I definitely get training and validation loss and accuracy per epoch. And maybe a little bit more user friendly, but just in general, the demo doesn't work as good as the PyTorch as far as resolves and
Yeah.
consistencies.
And Keras was written by one of the guys who was on the TensorFlow team, and it's it was ported or promoted as a front end for TensorFlow, but not sure. I don't know why. There must be something going on there that didn't become as popular as PyTorch, but I don't know.
Yeah, and I guess reason number two is basically it's a classical world with programming. So no matter what you're going to use for a device simulator, QPU, you could do lots with simulators today. It works within Python notebooks. As far as I know, most if not all quantum code is in Python. Written in Python. This particular part is written in Python. I have to install, or I'm sorry, Penny Lane, import Penny Lane code.
Yeah,
So
it's definitely the dominant language. I mean, there's Q Sharp, there's Circ. I guess Circ is actually a Python framework also. There are some other languages, but none of them have really caught on. But I guess the alternative would be Q Sharp. Actually, there's Java frameworks for
Here's
quantum.
one. I yeah,
Yeah, but
it's just
yeah. So I don't know how popular it's come, but the cool thing about that framework is Java seems to have become the language of the financial industry. So it could be a bridge there.
yeah. I keep talking to Johan about that every once in a while. I say,
Yeah.
shoot an email and ask him when is he going to let you write a compiler for it.
At this point, I don't know if I'm that interested anymore because nobody seems to be interested in
Yeah, I don't know.
in a specific language or in a new domain specific language just for quantum. But what he and then what was happening is it was Quantinium had their ticket framework. You probably have better luck building a plugin so he could plug into the front end of ticket, because then you could write your code in Java and distribute it anywhere.
Yeah.
Put it out to any of the machines. So,
Java.
but I haven't heard much from them lately either. Quantinium has not been reaping the rewards so much these days.
yeah, I think it was today, said they're doing QML. I actually asked in their ticket Slack, which isn't too busy these days, and I asked, what's the best way of going by doing ticket with QML, and they said that's not really our plan. And that was probably 2-3 months ago. And then all of a sudden I see in the news today, and you have to have something that just works. And I think that's what they're doing.
Do you know what's going on with what's the name of the company? Oh man, why can't I remember it?
What do they do?
They have this platform. I'm not gonna I'm gonna look it up for a minute while you. When was the last time?
Yeah, as far as I know, so IonQ they use emulators or simulators with Dell, so it's like a working technology. So I think the thing that's like a lot less public is how, what exact application are they using this quantum algorithm with GPUs? So like I said, like no matter what device you're on, it's a quantum algorithm. And it'd be interesting as this further develops, what they're saying, because even Google Bard, they say they're using QML, classical processing, these types of things. And Sandbox AQ, they went on a spree like in November with all these announcements, and even Tensor Networks, which is a way, to get more qubits out of simulators too. So.
Yeah. Yeah, but I mean, the like IonQ and Quantinium, I think they're struggling with their quantum computer width. I think they're struggling. They're hanging out at around 32 qubits or something like that, physical qubits. But so at that point, you might as well use a simulator because it's going to be faster.
Yeah, I think that they do that. I think they don't have an issue with software, as far as like,
Yeah,
that's not the issue that I've heard. And it's more like, if they can run on any device, I think that's what they're doing with Dell, do it. So,
yeah.
Question is Classique. Have you heard anything about that?
Oh yeah. I got a certificate. I haven't heard from them since the war started. I actually got a certificate from them the day before the war started.
Oh, really? I
Uh, that's a really nice platform.
that's right, yeah. I just visited their Slack community and noticed that they're doing hands-on workshops for universities. I just hope
Yeah. Oh,
to our university without protests.
yeah. Hopefully they were, they're based in Israel. I don't know if they have figured out a way to just migrate out of country. Um, but it's a really interesting platform. Instead of attacking things at gate level stuff, you basically go. They have this framework where you go in and you kind of describe the algorithm you're looking for, and they've got these templates. You pull up a template and you fill in the template, and the thing goes and generates a circuit for you.
Yeah.
And then the other cool thing is once you've compiled a circuit, they have a mechanism where you can send it to multiple back ends simultaneously. You can send it to IBM, you can send it to Penny Lane, you can send it to Azure, and that's a really neat feature if you're really trying to differentiate the platform's performances. But it's a pretty cool platform.
And you can see the circuit that it generates.
Yes, you can.
And
Yeah.
they have a really nice way of collapsing and expanding parts of the circuit.
Yeah. Yeah.
So do you know, as far as, because you say it's gateless model, like how is the algorithm written?
It becomes a gate. They take high level request and
Yeah.
to a gate. Gate
So
model.
like if you want to do one of the simpler ones is like, I want to do a Grover's circuit. It pops up this thing and you fill in the parameters for the Grover circuit and it builds you a Grover circuit with those parameters. It's like you don't even have to think about you don't have to go write any code to line the gates up. Like in Qiskit, you have to basically script the position of every gate in the timeline. This thing just does it based on the parameters you give it.
Oh,
Saves a lot of time.
okay.
I'll have to look into it more. Now, do you mean numbers of parameters that you want?
Well, no, the parameters are related to the algorithm. So in some of them you might stipulate how many qubits you want, but most maybe that is one of the parameters. It's like I want 8 qubits and I want this circuit to perform to these parameters. The parameters are for the algorithm, and then based on those parameters, it synthesizes the circuit for you. So, and they have quite a bit of stuff there. I mean, if you look through their catalog, there's all sorts of things they've already done.
Awesome. Any other last questions or comments? Good discussion today.
Yeah, another good presentation, Kevin.
Thank you.
I don't know when you sleep.
It's Chipotle time. So this has been discussion 117. This is Thursday, January 11th, 2024 for efficiency metrics and single and parallel quantum algorithms. Appreciate everybody coming on. Have a good rest of the week. Have a productive rest of the week.
And you didn't give us the star date.
Yeah. Take care, everybody. Appreciate it.
See ya. Bye.